Okay, this video is part 2 in a series on electric power system stability, and we're going to be writing an application that simulates the response of a electric system generator to disturbances in the power grid. And we're going to be writing a solution method to solve some of the differential equations in C#, and we're going to be using some numerical analysis methods such as Euler's method, Modified Euler's method, and also the runge-kutta method. So in the previous video, and I strongly recommend you take a look at that so you can understand the basic concepts behind what's required to solve this. But we talked about how the response of a generator, the speed and the acceleration of a generator, is dependent upon the difference between the mechanical power input to the generator, mechanical power into the turbine, versus the electrical power out of the generator. If the electrical power out is equal to the mechanical power in, then there is no change in speed. And this equation here we saw in the first video describes that. So the challenge here is to figure out the response of the generator to changes in electrical power on the power grid. Now here I've got a graph that we looked at last time of speed of the machine versus time. And if you look at this solid red line, this is a graph of the speed versus time response of a generator. And you can see that up to this point where this dot is, it's going along at constant speed. There's no change in speed versus time. At this point, we apply a disturbance, and suddenly the speed of the machine increases exponentially along this line. Now, what we need to do is we need to simulate this, because unfortunately we don't have this curve. We don't have an equation that says the speed versus time for this machine, for this disturbance, will look like this, and we just plug in the values of t and we'll get the values of speed. We don't have that. So as we mentioned in the previous video, all we have is these differential equations. And what that gives us is, once we put in a value for electrical power, it gives us a constant number which defines the slope at this point. So at this initial point, we know the electrical power out of the machine. We've solved it from a load flow, and we plug that in. We will get a number that represents the slope at this point, the slope of this curve at this point. So the challenge is we've got slopes, but we don't have the actual curve. So somehow from slopes, we have to figure out what the value of this curve is. So we talked about before, okay, we've got this line that defines the slope at this point. Well, we can use that line and we can extend it out here and use it to get an estimate of the speed versus time at this point in the future, at delta t ahead of where we are now. Now, it's not going to be an exact number, it's going to be an estimate. But at least it will give us a number that we can use. And once we're here, we've got a new speed at this future time, a new estimate of speed. And when we've got that new estimate of speed, we can then calculate a new value of electrical power and come up with a new slope at this point and get a new estimate, and we can keep going, and hopefully we will get a reasonably accurate reproduction of this actual curve using only estimates from the slope values. Now, up to this point, we've been talking about speed versus time related to the electrical power out of the machine. We also need to talk about the angle. Now, all machines on the system rotate at about the same electrical speed. Now, in the US, that's generally 60 hertz. In Europe and other places, it's 50 hertz. And that's called synchronous speed. So all machines are basically producing in the US a 60 hertz sine wave, and they're all kind of locked in together at the same electrical speed. Now, the mechanical or shaft speeds can vary depending on the construction of the generator. They can be, for example, 1800 RPM or 3600 RPM. But even with those different mechanical or shaft speeds, the generators are designed to give a 50 or 60 hertz electrical speed. So if they're all basically locked together, providing a 60 hertz sine wave, the only speed changes are oscillations around synchronous speed due to momentary changes in the electrical system. So if the machine is running at 60 hertz and something happens in the electrical system to cause the electric power out of the machine to go up or go down, that will cause a change in speed, but hopefully that will only be a transient disturbance, an oscillation that will stabilize and return to 60 hertz. So normally you're only going to see these oscillations, transient oscillations around synchronous speed. Now the purpose of doing these analyses to find out the transient response of a generator to changes in the electrical system is to find out if a given disturbance is small enough so that it doesn't really affect the generator and the generator can respond and recover and return to the 60 hertz electrical speed, or does it go out of synchronism? Is the disturbance so great that the disturbance causes the generator to lose synchronism, is no longer locked to 60 hertz on the electrical system, and it goes off and it's basically uncoupled from the electrical system? So the purpose for analysis is to find out for a given disturbance whether the machine can recover or else it will lose synchronism and become unlocked from the rest of the system. So we're going to need to calculate speed and angle and electrical power. Now, there is another differential equation similar to what we talked about for the acceleration of speed, and this describes the angle of the machine, and that is a function of the speed versus the synchronous speed. So the change in speed from normal synchronous speed defines the rate of change of the angle. Okay, so here's a second differential equation, very similar to the rate of change in speed versus time we talked about, and this describes the angle versus the speed. And we're going to need that because the electrical power out of the machine is a function of the angle of the machine. Okay, and here is a very important equation that defines the electrical power output of the machine in terms of the angle of the machine. And it's a function of the voltage in the machine versus the voltage magnitude at the receiving bus divided by the reactance of the machine. We'll talk about this, but you can see that we talked about we need to find the electrical power out of the machine. Well, that's a function of the angle, and the angle is a function of the speed. So we were talking about speed. We can come up with speed, and then we're going to have to calculate the angle because we needed to find the electrical power. So the generator angle is the angle of the internal voltage versus the rotating synchronous speed system reference. Basically, all the machines on the system are rotating at 60 hertz, and this machine generally is locked onto that, but it may have oscillations. So that is the angle that we're going to be looking at. Now, the power delivered by a generator is a function of its relative angle, and that is described by this equation here. So if we say that the voltages are constant and this reactance of the machine is constant, you have a direct relationship between angle and electrical power output. So a leading angle, if this angle is leading, it pushes power out of the generator into the system. If it's a lagging angle, lagging behind the system angle, it receives power. Okay? These are very important equations, and we're going to have to solve these in order to simulate this generator's response to electrical disturbances. So here is the simple model we're going to use of the generator. It's called a classical model of the generator. And here is the generator that has a mechanical input. This is the shaft input, the mechanical power input that is turning the generator. And the output is the voltage, the electrical power output, which is shown here. And the generator produces a voltage, which has a magnitude shown here with an angle. So it's V1 is the voltage of the machine at an angle delta. And here is the reactance we talked about, this reactance. So we've got this V1, V2 over X sine delta. So the reactance is this X, and here's V1 magnitude, V2 of the bus that it's connected to, and the electrical power output defined by this. So we've got V1, which is this magnitude, V2, this magnitude, X is the reactance, and sine delta is the difference between the angle of this voltage and the angle of this voltage. Now we also have an inertia we talked about in the first video that we'll be using in simulating how quickly this machine can respond to changes. Now the other thing we're going to simulate here, we're going to use a simple model, and we're going to simulate a disturbance, and this disturbance will be a three-phase fault right at the terminals of the machine. And if we have a three-phase fault and tie all of the three phases together, the electrical power out of the machine going to the load is going to be 0. So you can see if I've got 100% 1 per unit mechanical power input, and suddenly we go from 100% electrical power to 0 electrical power, that's going to cause the machine to speed up during this three-phase fault. And then when we clear the fault, suddenly the power out is going to return and the machine is going to oscillate, and we need to find out if it can recover. Now here is a model that I put together in a industry standard software application called PSSE, and I've basically done this model. And you can see here I've got a response. I'm looking at the response of the machine, its angle and electrical power, and I'm looking at it for 5 seconds. Okay? And this graph down here, this sine wave down here, is the electrical power output. And you can see it starts out at just under 2 per unit under normal steady state load flow. Suddenly we apply a three-phase fault and the power out goes to 0. It maintains the three-phase fault for 1/10 of a second. It gets cleared, and then you can see the electrical power output oscillating continually through the 5 seconds. Now also we're plotting the angle, and you can see it starts out about 8 degrees. So this is important to do this, to put your model together on an industry standard simulator, so when you write your code you can make sure that your results from your code match what you got from the industry standard simulator. And what I'm going to do is I'm going to show you the results I got from the code I wrote here and show you that, well, here's what we got doing a simulation in C, and you can see that it matches very closely what I got in PSSE. Okay, I've got maybe a little over 2 cycles in 1 second of oscillation, and that's about the same. And you can see I go from normal to 0 electrical output, same here. So you can see that it's very close. There's a little bit of difference because of my initial values are a little bit different, but basically we're going to write an application that looks like this and gives you the output of the machine. So what we're going to do is step back and go through some of the methodology that we can use to solve numerically this response of the machine. And we started off before talking about the slope. And all of this numerical solution is about slopes. It's difficult to think at first about slopes when you're used to having an equation. You fill in the values and you can just plot the equation to get the answer. We don't have that here. We just got slopes. So all of this numerical solution is about slopes. So you have to keep slopes in mind. So what we do is first we solve an initial condition from the load flow to find the electrical power output at time 0. And once we've got that electrical power, we can get the slope at time 0. And that's that line here. We're going to use this line to get an estimate in the future. Now the question is, okay, we've got this slope that we defined at time 0. Is there a more accurate slope we can use? Because if you look here, if I go out here and I come up with an estimate for speed at this point, Yeah, it's better, but it's really not very accurate because the actual slope or the actual speed is up here somewhere. So is there some way for me to get a better estimate of slope? So the different numerical methods for analyzing these differential equations involve different ways of coming up with a more accurate slope to put us out at a more accurate place on the curve for our estimate in the future. Okay, this one is not very good. It would be nice if we had a slope over here somewhere. Okay, if we could get a slope that brought us over here, we'd have a much better estimate. So all of the Euler's and runge-kutta and other methods for numerical analysis involve ways of coming up with better and better slopes. So it will put us at a better position to get a future estimate. So again, here we are. We're starting out here with our initial slope. We solve for the electrical power output. It gives us a slope. This power is a function of angle. Remember we said it's a function of angle using this equation. And that angle is a function of speed using this equation. So we've got a speed. We need to figure out the angle, then the electrical power to get a better estimate. Okay, so these are the three equations we need to solve to get better and better estimates of our response of our machine. So we have our slope here. We go out to this point. We get a new value of speed. We plug that speed in. Using that speed value, we come up with a new value of angle using an estimate. And from that angle, we plug it in to get a new electrical power. And then at that point, we get a new slope at this future point. And then we have this new slope which says, hey, this is better than this slope. So maybe I can use this slope along with this slope and maybe take the average of the two to get a better estimate out in the future. So let's look at the basic design for an application to simulate the transient response of a generator and basically step through and see how we would put it together to solve for transient response. So up here, the first thing we need to do, like we said before, is run a load flow and find out the electrical power output of all the machines. In this case, we're just going to have one machine. So the electrical power output, we've got that at the initial time, and we can use that electrical power output to solve for the slope at the initial time before the disturbance starts. And we plug that in here. That will give us the slope of the speed time curve. And once we've got that slope of the speed time curve, we can figure out an estimate for speed, plug that into this equation, which gives us a slope of the angle time curve. So it's basically the speed relative to synchronous speed. So now we've gotten estimates for the slopes of the speed and the angle curves. Once we've got that, we can get estimates for speed and angle at t plus delta t, which is the time step into the future. We can get new estimates for the speed and the angle, and then we can apply the fault. We can make whatever changes to the electrical power system and calculate the new electrical power out of the machine based on what happened. In our case, we put a three-phase fault, which means the electrical power output goes to 0, and now we've got a new value of electrical power output. Once we've got this new electrical power, we can go back to the next time step. We've got the electrical power, and we do the same thing. We calculate, using this new value of electrical power, calculate the slope of the speed time curve. Using that, we can calculate the slope of the angle time curve. And then we keep going and keep calculating using these new estimates and find the speed, angle, and electrical power of the machine versus time. Now here graphically is what we're doing. We're starting out at this point, normal conditions, starting out to the initial time before we start the disturbance. We've got the electrical power output, we've got the speed is constant. And then what we do is we use that electrical power to solve for the slope. And we've got this slope now that looks like this. And once we've got this slope, we can go out to get a new estimate for speed out at this future time. And once we've got that, we can calculate a new slope, and we can get a more accurate estimate for the curve, the actual curve at that point. And we keep going and doing that same thing until we have simulated the response of the machine. Okay, so using that design, let's write a C# application to simulate the single machine. Now, I showed you before, I've got a application here, a single chart, 2 buttons, and I press solve, and it basically just applies a 3-phase fault on the machine for 1/10 of a second and clears it, and the electrical power oscillates and the angle oscillates. And I've got an exit button here. So here is the event handler for the solve button. I've got right here, solve. And when the event handler just calls 2 methods. One is initialize and one is the modified Euler method we'll talk about. Initialize is this method right here. And all it does is goes through and populates arrays for the machine electrical power, the machine angle, and the machine speed. And it uses the initial steady state values for equal to the mechanical power, the initial angle, and the initial speed, which is just synchronous speed. So it just populates everything up to the point where we're going to apply the fault. So now, once that's all initialized up to the point where we apply the fault, we'll call the modified Euler method to solve for the response of the machine as we apply the fault. So here is the modified Euler method to do just that. Now, before we do that, we've set up some initial conditions and solution parameters that we will need, variables for this Euler method to work. So the first thing we've got up here is some variables that we have set out to define the solution and iteration parameters. So here I've got a T max, which defines the total length of time we want to simulate. In this case, I want to simulate from 0 to 5 seconds. Delta T is the step size, and here I've got 1 millisecond. So I'm going to have 5,000 samples spaced a millisecond apart. And here is just an integer of those 5,000 samples, T max divided by delta T. And here is the start and end time for the disturbance. I've defined it as I will start at T equals 0.1 second. I'll apply the fault. I will stop. I will remove the fault at time T equals 0.2. And here I've just got some other internal variables we're going to need to do the solution. Now the next thing, I've got to define some machine parameters and initial conditions. I've defined an H value, which is the inertia of the machine, as 10. And usually an inertia is generally in the range of 5 to 10 is a typical value. Machine reactance is 0.1 per unit. You can change it to whatever you want. You can change the inertia whatever you want. Initial mechanical power is 1 per unit. And under initial conditions, the electrical power is the same, so it's a constant speed. Initial angle is whatever you want. I've just calculated initial angle based on initial electrical power of 1 per unit. Voltages are 1 per unit, and the machine reactance is 0.10. So I'm just taking the arc sine of the angle, of which is 0.1. And then the set up the initial power of mechanical power. And here I'm setting up the synchronous speed in radians, which is 2 pi times f. So I've got a frequency of 60 hertz. And then the initial speed is equal to the synchronous speed. And here I've got a damping factor we're not going to use, but we can use that in the future. And here is a constant that is basically just the synchronous speed divided 2 times inertia, which you may recall from our, for calculation of d omega dt. We're going to use that as a constant. So now I've got everything initialized and set up. All I need to do is define these arrays of machine angle. And it's an array that has samples number of elements. So in this case, it's going to be 5,000 elements. So it's machine angle, machine speed, and electrical power from the machine. So now I've got everything initialized. I can go in and start solving. So I've got a couple of internal variables. Angle previous equals angle initial value, takes the initial angle and uses that as the previous angle. And I've got these values you can use. So here is where I actually do the iteration. And here I have set up a T1. And this is the starting time for the actual simulation. Recall, we already initialized the arrays up to the point of starting the disturbance. And this gives us the starting point, the starting time of the disturbance. So we will start simulating from that disturbance time. So the array values will be starting at T1, which is the number of samples times T start over T max. Okay, so I will be probably starting at array value 100 or something here. So now I'm starting at this initial point, and we're going to first find the initial slopes. You recall we were going to calculate the initial slopes. Here, we calculate these slopes for the omega and speed. So we start, we'll call those K1D and K1W for delta and omega, and that is speed previous minus speed sync, and omega is A, which is that constant we defined, which is proportional to the inertia, times PM, which is a constant, minus the initial power. Okay, so we've just calculated these two slopes. So now that we've got the slopes, we can go out to T plus delta T and get estimates for the angle and the speed. We'll call them new angle and new speed. And it's equal to the initial angle plus delta T times this slope. So you can see we're solving for angle and speed simultaneously. And we are going out to this new T plus delta T and getting new estimates for angle and speed. And once we have those, we can apply our disturbance and calculate the machine power. So if the time is during the disturbance, which is greater than T start and less than or equal to T stop, then we are saying that the power, the electrical power out of the machine will be zero. We're applying a three-phase fault, so the electrical power out of the machine will be zero. Otherwise, if it's past the disturbance time, if the fault is cleared, the power equals the calculation, which is 1 times sine of the angle over x machine. Okay, it's basically just this equation that we're solving for right here. We're solving for the electrical power using this latest value of angle. Okay, so now that we've got the new calculation of power, we can go into what's called a corrector step. We use these predicted values of power and speed and calculate new slopes at the future point. So we're going out here to get this new slope at this future point. So here we've got K2D, which is the rate of change of speed at this new point, is the new speed minus synchronous speed. And rate of change of speed is equal to using this new power. And here's where I put in this damping factor. You can ignore this, but will allow you to have a damping factor. But basically, we're just going out to this new point at T plus delta T and using the new and coming up with the new slopes at that point. And using those slopes, now we come out with new values of angle, speed, and power. Now, what we've done here is we've come up with two slopes. We've come up with a slope. We have our initial slope here, and we just came up with a second slope here, which is a more accurate slope that we came up with at T plus delta T. So now we have two slopes we can use. We have K2D and K1D, K2W and K1W. So what we can do is we can take the average of those two slopes to get a more accurate slope to use to get our final estimate at T plus delta T. So all we're doing is we're taking those two slopes, dividing by 2, this 0.5, we're taking the two slopes, we're taking the average of those slopes, multiplying times delta t to get a new value, in this case of angle, and we add that to the old angle plus the new angle, and here's our final estimate of angle. Same thing for the speed. We take the average of the slopes times delta t, add that to the previous speed, and we get a new speed. So at this point, we have come up for that iteration, we have come up with a new value of angle and speed, and our power is just whatever this new power is that we calculated up here. So now we have got a new estimate at this time step, and we can move on to the next time step. We've basically completed this. We can go on to the next time step and do it over again. Okay? So that's basically the methodology we use to do what's called a modified Euler method. So now in the next video, we'll talk about a more accurate method called runge-kutta, fourth order, which instead of taking two slopes like we did here, it comes up with 4 slopes and takes the weighted average of 4 slopes to get an even more accurate solution. And it's a bit of a modification of the modified Euler we used, and we'll talk about in detail how to write code to come up with a runge-kutta. So I hope this helps. Take care and have a really good day.